Um, Good afternoon, all, and I welcome everyone for our group colloquium. It is my pleasure to introduce our speaker today, Professor Xiang Zhang from Coventry University, UK. She is going to deliver the talk on fatigue and fracture behavior of additively manufactured titanium alloys. Professor Zhang received her PhD from Imperial College London. She has over 35 years of experience in research and teaching at various UK universities, such as Imperial College London from 1990 to 97, Cranfield University from 97 to 2014, and Coventry University since 2015. She is a chartered engineer and a fellow of Royal Aeronautical Society. She currently serves as an editorial board member for a number of scientific journals. In 2016, she was awarded with the Helmholtz International Fellowship. Her research is mainly on the mechanical performance of engineering materials, with a particular focus on the fatigue and fracture behaviors and development of predictive models. She is fluent in both metallic and fiber reinforced composite materials, primarily for the aerospace applications. She has published over 250 papers and supervised 30 PhD students. In the last 12 years, she has mainly studied additively manufactured metallic materials. She is going to give today lecture on fatigue and fracture behavior of additively manufactured titanium alloys. Professor Zhang, thank you very much for giving us some of your time, and the floor is yours.
Okay, thank you, Prakash. Can you still hear from me?
Yes, yeah.
Okay, thank you for your very kind introduction. So I'm going to talk about fatigue and fracture of titanium alloys made by additive manufacturing technology. And my name is Xiang Zhang, as introduced, but I would like to acknowledge my two key colleagues, Abdul Syed and Bilal Ahmed. They both have worked for this for the last 10 years. And then there is a list of people I want to thank. They are mainly my PhD students and colleagues. And the last but not least, two collaborating universities. Cranfield University made all these samples, and the University of Manchester Materials Department, Professor Phil Prakash guided us on microstructure analysis. So I just have a very few slides to show the materials engineering research group, what is our mission or purpose. We develop and apply advanced experimental methods and computational methods to the study of structural integrity problems, particularly in the high-value safety critical industries, which are the aerospace and the nuclear power industry. And we work with global partners in industry, academia, and the national laboratories. Currently, we have about 10 academics or researchers and 20 PhD students. So just a few slides to show the equipment. We feel we are quite unique. We do residual stress measurement, and the first picture you see is by diffraction mechanism. So it's the laboratory-based X-ray diffractometer. But the thing for this is I want to show is they all got a robotic arm, so it can measure 3D shape. The picture in middle is actually a cruciform weld from TWI, and we were detecting residual stress. Then there's also a complementary tool. It's called incremental hole drilling. By drill tiny small holes, it's not destructive, but it can verify the XRD. And we also use a destructive method. I think we probably the doing quite well in UK on the contour method. And basically on the left is electrical discharge machine, and then the middle is a coordinate measurement machine. Then on the far right, the specimen contains residual stress. By doing a very controlled contour cut, the profiles being produced are really caused by residual stress release. So combined with finite element, residual stress can be measured. The reason we're doing this is for very large scale or thick structures. You either have to go to neutron facilities, national facilities, or even neutron will be restricted by a texture microstructure features. So we always like to verify by a destructive method. So the two very good examples on the lower left is a benchmark beam for many laser powder beam fusion manufacturing, and that will determine the residual stress distribution. And that was done by Professor Mike Fitzpatrick's team and agreed with neutron with finite element analysis. On the far right is a very complex cruciform made by Cranfield by wire directed energy deposition, and the residual stress was measured on the lower right, then verified by neutron diffraction in ICES. So the final slide to show our equipment is a material testing. We have about 8 of these different test machines, and on the horizontal axis, the loading range is between 10 kilonewtons, 3 kilonewtons for polymer, to up to 250 kilonewton capacity. Then we can also test the strain-controlled fatigue, and also high temperature up to 110, and this is mainly for nuclear materials research. So then finally, there's a material characterization. We have this optical scanning electron microscope, but also have a nano indentation atomic force microscope. I think every university has these standard facilities. So my talk content today is I really want to go through all the mechanical behavior performance and the designers would like to know in order to use additive manufacture material for load-bearing safety critical structures. So I will go through tensile fatigue and fatigue crack growth rate, and also whether residual stress has a role or residual stress can be neglected. So I mainly will focus on the effect of defects and the microstructure effect. So just a few introduction, 1 or 2 slides on additive manufacturing of metals. I think most people are very familiar with this. I just run very quickly. The first one is a laser powder bed fusion. Then the other version is blown powder directed energy deposition. Then the third one is wire arc directed energy deposition. The old name for this is wire arc additive manufacturing, also called WAM. And I've been mainly working on the third one in collaboration with Cranfield for the last 15 years. In terms of the difference between the laser powder bed and the wire arc additive manufacturing, the key difference is their cooling rate. And as you can see, the cooling rate for the laser powder bed or the electron beam powder bed fusion is at least 1 or 2 magnitude slower than the cooling rate. Sorry, faster than the cooling rate of the wire arc version. The advantages of the laser powder bed fusion is they have very good layer resolution, up to 0.1 millimeters, so they can make a very so-called the near net shape component. But for the wire arc additive manufacturing, the layer resolution is about 2 millimeters, and even worse for steels. So some materials will be removed from the surface and the roughness issues. So most of my research are related to wire arc DED. So my talk today will be focused on this. There will be 1 or 2 slides on the laser powder bed fusion. So the business case for titanium, I think I should add a word, is the material is very expensive and it's very hard to machine off, and also very expensive to discard by machine a very big forged sample into a tank like this. So you would need to machine off 80% of the material, very expensive titanium. So there is a business drive for this. So Cranfield has made a satellite propeller tank just by welding the wire layer by layer, 2 halves, then they welded them together. It was tested in Sheffield for the proof strength. The benefit of this is the cost reduction by 50% in terms of material usage. The lead time from years to weeks, they claim, and also is a bespoke geometry for each space mission. Just want to say, if you want to make this for cars, probably not worth it, as you need millions of them. But for space launch, you probably just need 12 or 20. So additive manufacturing can really save money. 2 more examples on large structures. The advantage is 100% utilization of the raw materials and the bespoke geometry. So from the left to right, they have made a fuel tank for the space applications by welding thin titanium wires layer by layer. And also the BAE systems working with Cranfield made a landing gear by rib. So they claim 50% reduction in the cost compared to machining off from a forged block of materials. And then they made the largest structure component as a demonstrator. So it's several meters long and held by the whole group of Cranfield Manufacturing Center. In the middle is Professor Williams, who leads the center. So I was very fortunate to participate this EPSRC program grant for the last 6 years. And that was led by Cranfield University and with partners of Manchester, Strathclyde, and Coventry University. We each lead one big research theme, from process development to materials science and the physics-based process. And I also, the last one, I lead the structure integrity and the quality assurance research. So the project has just finished in last year. The website at the bottom of the slide, you can see our research. So most of the topic I'm presenting today are from this research program grant. So the challenges to structure integrity using additively manufactured structure materials, people often say this is 3. One is residual stress, so they're already there and often in tension, and the red, and balanced by the blue in compression far away. But usually the tensile stress is at the geometry change. So people obviously think this is an issue. The second is heterogeneous microstructure, typically presented by the columnar grains during the additive manufacture. This vertical direction is the material build direction. Also very strong crystallographic texture. Then the third one is the defects. So by optimize the process parameters, the lack of fusion by low energy and the keyholes by excessive energy can be controlled after so many years of additive manufacturing research. But one of the defects cannot be completely eliminated is entrapped gas pores. So we will always find this. Are they critical to fatigue? And this has been my research topic. So the problem of all of these is they do cause anisotropy in the mechanical properties. So the loading direction in the material direction or transverse to the direction would be different. So which design allowables people would use. And also they cause very large scatters, much larger than casting and wrought materials. So this is my quick introduction. I will just move on to experimental method. Then I will talk about mechanical performance one by one, from tensile to fatigue to crack growth to toughness. So the experimental method is, I just acknowledge Cranfield made all of these samples for us. If the samples are thin structures like aerospace, they just use single pass weld. If the samples are thicker and they try the parallel pass, 4 times of welding for each layer or oscillation. I think the conclusions currently after 15 years, they would prefer oscillation build and the single pass. Then for the grain refinement, this is to control the columnar beta grains in titanium, just to make them more equiaxed, so to have material properties and to reduce the anisotropy, to reduce the design allowable, the scatters, the design allowables. So they have tried the interlayer hammer pinning or rolling, layer by layer, but they also tried thermal gradient control. And the second one would be cheaper, not involving any mechanical deformation layer by layer. So then they also tried post-process annealing to anneal the material to above the beta transit temperature for titanium to introduce beneficial lamellar large colony structures. I will talk about this. Then they also studied the global versus local shielding. And so the picture here actually shows the hammer will drop on these walls here. And so every time you build a layer, the hammer will pin. So in terms of my material samples, all I receive is what I call walls. We all call this walls. So if you see my slide, the wall is quite big. It's like 100 millimeters by another 200 millimeter long, 100 tall. Then we extract these dog bone samples, either in the build direction or horizontal to the build direction for tensile and fatigue, S-N curves. But we also working on fracture mechanics properties. We use compact tension specimens and for fatigue crack growth rate, and also measure fracture toughness for crack either parallel to the layers or transverse to the layers. So in terms of residual stress evaluation, we use our in-house facilities, but we also go to the national neutron facilities. And we also use a contour method to check the through thickness change. So before I talk about mechanical properties, I really want to show how big issue is residual stress in the wire DED problem. We always have a residual stress. The horizontal material is a substrate made by wrought materials or forging. Then the verticals are walls. So these 110 millimeters are 140 layers or more. So we studied the Ti-64 and also Ti-64 with interlayer hammer pinning, and also a low alloy steel, ER70S steel. And this is very weldable, and also the offshore energy, people like it to repair or to cladding their corrosion damage, for example. Then we also measure the Waspo alloy. This is a new name. I think it's mainly nickel-based with some steels, but all of them show the red zone is at the intersection with the substrate. Then there's some compressive stress to balance it. So the measurement really agree with the theoretical formula by Professor Williams and his colleague. There are two separate papers, quite well known. They basically say residual stress, the arrow to the left, to the right is tensile and balanced by compression, and that bending moment is balanced by the reverse bending of the substrate. And the two papers on the far right, lower right, were written by my student or postdocs. It's mainly to model a thermomechanical model to understand this. So this slide is quite important. What I really want to say is in the wall, residual stress is quite high. It's about the yield strength of the material. But when you actually extract these very small compact tension samples or tiny small dog bones for tension, all of them are released because there's free boundaries. There's no material to hold the residual stress, so they are released. So the maximum stress distribution from the notch root of this sample to the edge of the sample is actually below 50 megapascal, and that was caused by the notch root stress concentration. It's not a real residual stress, because we also verified this by not having a notch and just a tiny small block extracted from the great walls. And we found in this paper 2022, residual stress are relaxed. So what I want to say, the third bullet point, the mechanical properties we presented today, I present today, are materials' intrinsic properties. This is in contrast with the powder bed fusion material because they only make near net shape material. They have the additive. They don't extract samples. They may polish the surface to remove roughness, and they may just remove tiny small layers. But for the wire arc DED, we actually extract the samples. We extract many of them from one wall, so residual stress are released. So the material properties I present today can be regarded as the intrinsic property, only reflect the additive manufacture materials microstructure effect and the porosity effect. So with that, I just have one slide to show. We also, in the methodology, we probably the first people about 10 years ago, we embedded gas pores on purpose. So for the wire arc additive manufacturing, can someone confirm you can see the mouse movement?
Yeah.
Okay, so for the additive, for the wire arc additive manufacturing, we use a clean wire to produce the samples on the left, but we also use contaminated wire deliberately with some greasy oil, and we produce the gauge length of our tensile samples. This has been a real problem for people not using clean wire. When they look at the fractography, they found more gas pores. So this was deliberately designed experimental work for PhD projects. So for the powder bed fusion, I participated in a project by the Manufacturing Technology Center, a catapult in Coventry. They actually use laser powder bed fusion, so that is near net shape build. They build so many, and these orange colors is we embed one pole, they call seeded pole, by computer-aided design. So in that layer, they don't print materials. Then they also in blue, they print a defects in the middle. These are not lack of fusion or keyhole. These are entrapped gas pores. And by computer tomography, it could confirm the pores are still there after the manufacturing. And this is a MTC lead project called Model Farm. So that concludes my methodology section. So now I'm going to talk about mechanical performance one by one. And the first one is the tensile, then fatigue crack growth rate. So I borrowed this graph from these publications a couple of weeks ago because I think it's very good. Show schematically, the black is the wire arc additive manufacturing. The red is the rod, and this is titanium. I forgot to type. And the main message is the strength is okay, and is even higher than the rod counterpart, but the ductility is much lower. And this has been the consensus for the last 10 years. People found strength is okay. And the reason for that is because the finer grains, much finer grains for the additive manufacturing. We also found this in our own research, and the warm Ti64, and the blue lines are the reference specimens, no defects. The dark red curves here are purposely built defects, so we have a control. We just have one or two, but we know they are porosity specimens. The conclusions bullet point is strength not affected by isolated pores, but ductility suffered significantly, which I will discuss why. And there's also very large scatter in additive manufacturing materials, even without the defects. So I will talk about this. And in the separate study of laser powder beam fusion Ti64, it's the same story. Strengths without defects and with defects are similar. They can reach 1,100 megapascal, but the elongation suffers. Without the defects, the black is the 16%, but with defects, elongation will be reduced. So what I quite like to say is it's not depends on how many defects you have. It always depends on the kilo one, and the location probably matters more. So I will conclude this after the fatigue testing section. So just say when we change it to a different material, we found the similar behavior. This is aluminium magnesium alloy with scandium, 0.3% scandium. The reason for adding scandium is to make it stronger and for space applications. And this is the PhD student I supervised just submitted. So the lower curves are without heat treatment, the upper curves are with heat treatment. But as we say, the strength is never having any problem. It's always okay. It's the elongation at failure. Very large scatter also depends on whether there's porosity or not. So the Warwick University manufacturing group kindly did the X-ray computed tomography for us. And this is the tomography graph. And you can see this is a 3D problem presented in 2D. So it looks like there are a lot defects. In fact, the density, the volume fraction is 0.04, so it's 99.6 dense. And the maximum diameter of any pores is 500 micron, and the average is about 70. Stress around the defects will raise by a factor of 2 or 4. So that can be coped by neighboring materials. So they all work together to reach the yield strength. But the defects will reduce elongation because there's no work hardening. Most aerospace material really lack of post-yield work hardening. So the elongation will suffer. So just switch to fatigue because I'm aware of the time goes very fast. Fatigue without defects, and this is a quite high quality build. We did a scan, we did tomography, we did a fractography, confirm maybe tiny small process inherent gas pores, but very, very small, smaller than critical value. And the message I want to show is the gray part is the traditional casted titanium 6-4. The pale blue shadow is the wrought by mill annealed. Then the blue and the orange dots are the additively manufactured, either in vertical direction or horizontal direction. The message to take home is fatigue strength is really okay. It's comparable with the wrought or even greater than the cast. And there's very mild anisotropy because of the columnar grains. So one direction is different from the other direction. But because titanium grains are very fine, so the anisotropy is much, much milder than steels. I have seen papers on steels. The anisotropy is very strong. So very, very small pores did not reduce the mean curve, but they probably caused the large scatters in the data. So I can elaborate this a little bit later after I talk about purposely embedded pores. So the first study we did about 9 years ago is we print gas pore in our samples. And we found that this is applied stress versus number of cycles to failure. The pale gray is the benchmark without porosity. Then the blue, we actually found some porosity, but it's our reference specimen without contaminated wire. But they do have naturally occurring ones. Porosity is much, much below 100 microns. The red ones are the pores greater than 100 microns. So my student, Dr. Biswell, published the first paper on this, just say the critical pore size is around 100 micron. Subsequently, I reviewed a lot of papers in steel and titanium. They do agree with this number between 80 to 110 micron being quite a critical defect size. The second student carry on with analysis. He actually say this very large scatter, if you see the 500 megapascal stress and also the 400 megapascal stress, the life has a scatter factor of more than 2 magnitude. It's not due to the defect size, but it's actually due to the defect's location. So the defects inside the material after machining into dog bone shape, they may be very near to the surface and cause very high stress concentration. So these open circles are surface defects, and these solid dots are the internal defects. So that's that contribution to clarify the location being the most critical for fatigue rather than size. And then the last study we did is the laser powder bed fusion, confirm very similar story. And the location, these black diamonds are all near the surface. We call surface pore or subsurface pore. But the the round ones are internal pores. So I think I just move on quickly. And we also did a tomography we call interrupted tomography. So after every 5,000 cycles, we stop fatigue testing, we do X-ray tomography, and we found the pronounced crack propagation from pore around the % of the total life. Obviously, this depends on the stress levels applied. What I really want to say from this fractography picture is to say there is always one killer pore. It's not depending on how many you have, and it's the killer pore, and also it's the location of that pore. So these big ones is in the bulk of the material, is almost like hibernating there, but the one very near to the surface is critical because the stress concentration is high. There's no material on the other side to carry the stress. So with that, I quite like to conclude that the tensile strength is very comparable or even better than traditional rod because of the fine grains in additive manufacturing. Ductility is affected by defects and due to lack of work hardening in titanium. Anisotropy is mild because titanium alloy has fine grains. So these findings I wrote in blue agree with independent research in literature. In terms of fatigue, it's all related to defects. So, and it's all related to one killer defect, and its location is much more critical than its size. So we actually, for our material, we show this is around 100 micron in terms of diameter by fractography. And this broadly agree with other people's findings. And so I think I will quickly move to my final testing, which is the fatigue crack growth behavior. So we have these very large walls. One is thin for aerospace applications. The other one is thicker for energy sectors. And we cut many of these small compact tension specimens with 2 crack orientations. So the broader picture is like this. The colorful symbols are additively manufactured titanium. And what you're looking is the crack growth rate, dA by dN, versus the control parameter stress intensity factor that take account of the crack length and also stress applied and the geometry. So the additive like actual manufactured material is in between of the traditionally manufactured titanium. So the mill annealed forgings has the fast growth rate, and the casting has the lowest one. And if we do a beta annealing for the mill annealed, the crack growth rate slows down. So I will show the next slides. These all rely on the microstructure difference. The traditional hot rod material has an equiaxial or globular microstructure. They don't stop crack grow. Crack can just go around them, around the grains. But with a beta annealing, you create a Wittgenstein microstructure, and that causes a lot of resistance. It's quite a large colony alpha las. So the crack has to grow zigzag around it. It's a lot of resistance. And casting being the best is because they have the similar Wittgenstein microstructure with very large colonies of the alpha las in the same orientations. For additively manufactured material, if we do a beta annealing, we could achieve this situation like the casting. But if we don't do the post-process annealing, it will be just like the ordinary lamella structure. So the microstructure really determines how fast the crack propagates. So with that knowledge, about 3 years ago, we started to study the microstructure tailoring. So by in-process pinning and also by post-process annealing. So the reason for this is to trying to make the columnar grains being equiaxis grain to have a good isotropic properties. I had 3 options. Manchester is working by adding tin content. Then Cranfield is doing a thermal control or rolling, and also thermal energy control and control the cooling rate. So these 4 pictures, I picked up the last one. So after pinning, the far left, the very long columnar grains become equiaxed grains, very small and hopefully it's isotropic properties. And so I just show you this one with pinning. We actually, after the beta annealing at this temperature, the microstructure become a large lamellar colonies, has a lot of resistance to crack growth. So before I show the crack growth, I just want to show you very quickly the optical graph on the top and the EBSD images at the bottom, and really shows the far left, you get large columnar grains in the as-built condition. After pinning, they are equiaxed grains. Then after beta annealing, the grains grow double size from 1 micron to 2 micron, but still equiaxis. And then the good thing about annealing is to create large lamellar colony microstructure to have more resistance to crack growth rate. I skipped the tensile. I just want to show tensile did not even suffer by beta annealing. But crack growth rate, in terms of the crack growth rate against the driving force stress intensity factor, the blue curve is what we are going to concentrate. The orange and the black I showed before is between the traditional casting and hot rolled material. But the blue actually very, very slow, the growth rate. On this log scale, the difference is 1 magnitude, and that is very good news for damage tolerance design. Another good news is the starting point for crack growth. The threshold value, delta K threshold, is delayed by 3 times. So the crack growth will not onset until much late. On the right basically shows the as-built and the pinned has relatively smooth crack growth because it's not a colony microstructure, but with beta annealing, a lot resistance were created. So there's crack deflection, there even secondary cracking, branching. All of these absorb the strain energies, and which would be otherwise being consumed in crack propagation. So I think I just skipped this. I have basically said all of this. So another example is to show the story is the same for Ti6-4. Previously, I showed the Ti6-242 is a high temperature titanium, and shows with beta annealing, there are a lot of resistance to crack propagation. So I think I just summarized this fatigue crack growth rate for the wire DED. I have a typo wire arc DED is between the mu annealed and the beta annealed forgings, and is highly dependent on microstructure characteristics. And because of this, we can just make use of this by tailoring the microstructure to achieve high damage tolerance. So I don't think I have time to talk about modeling. I can leave my slides here, and I think I should leave 10 minutes for questions. Is that okay?
Yeah, perfectly fine. Yeah.
Okay, so I have a few modeling slides, but I think we probably can talk about it later. So I want to thank you for your time.
Oh, thank you. Thank you so much. Thank
Yeah.
you for a wonderful talk with the methodical way of studying the porosity effect and anisotropy, all this on the mechanical properties, especially fracture and fatigue behavior. I think questions are coming from audience. Harry, please.
Yeah, so thank you very much for the nice talk and very informative talk. I just have a question that in many cases when we make additively manufactured components, they are hot isostatically pressed to seal up the pores. Have you tried something like this?
Yeah, that's a very, very good question, Professor Harry. The powder bed fusion people always do that because they have a very turbulence in their build chamber. They have entrapped gas pores. And for Cranfield made wire arc additive manufacture layer by layer, they probably overlapped a lot. And so we don't find it necessary for titanium. However, they do it for steels.
Okay, thank you.
Yeah, so that is very important. And also the MTC people found the HIP can shrink the entrapped gas pores, but may not be completely closed yet. So with elevated temperature loading, they may open up. And that is not my area, but I have seen these papers. But HIP is a standard for powder bed fusion.
Thank you.
Yeah.
Yeah. Alphonse?
Hi, this is Alphonse from GK Aerospace. I think
Hello.
just before asking my question, maybe just to Professor Hari Badesha, I mean, the wire arc additive manufacturing and the laser metal wire deposition from GKN, we aim a very large part, Professor, like kind of, what we have laser wire deposition about 6 meter by 3.5 meter. The hip vessels today is suitable for powder bed, small complex shape, which is like 500 by 500, or the world, I think, biggest hip vessel. I also explored about, I think, 3.2 meter wide and 1.5 meter or 2 meter tall. So the component like aerostructure, large titanium structure, if you look out and solution, hip as a solution, it doesn't work out in a practical way because we look for a large scale structures. And then just coming back to my question, I think you did mention, in terms of fatigue crack growth rate, Professor Zhang, like you did as built and then peened and then beta anneal, peened plus beta anneal. And what I wanted to say is peening is good. I think again, I'm from industry. Please don't take it the wrong way that peening works in a simple linear. Otherwise, it takes a lot of time as well. Your productivity gets affected. But if I want to make a large structure, I want to, just completely avoid like peening. Again, peening also in titanium. When you peen in a large 2 millimeter bead wide, the top surface it introduces some deformation. But then when you deposit the next layer, half of the deformation that you introduced is just again goes to liquid to solid transformation. Again, it's just you don't really get the. I mean, you do get some benefit, but what I'm not saying. The main concern I have is the productivity goes down. So I'm thinking, is there any kind of like heat treatment even without introducing deformation? If you do just as deposited some heat treatment, have you seen anything like improving fatigue?
That is a very, very good question. And we tried Pi 6.4 without the pinning, but just add beta annealing.
Okay.
And there are some benefit, but the Kluman grain is still there. And I think talking to aerospace industry, they also care about the property anisotropy. So their design allowables, they probably want to apply load in other direction or 45 degree. So yes, we did test that one. We thought we could just by doing beta annealing without interlayer pinning, but the result shows some benefit, but not a lot of benefit. I can send you the data slides to say actually how much. I just take a note. Also, another comment you made is very good. Pinning being not practical also slow down the production. So the other two options currently is adding tin, TIN by Manchester, and the Cranfield is trying to control the thermal input and the cooling rate. So they think if they get the physics right, the the columnar grain maybe not grow.
Okay.
Theoretically, they argue this is possible. So I can check how far they have gone, then
Okay.
I can brief you as well. I know you work for GKN, isn't it?
Yeah.
Yeah.
I'm Phil Pragnell's
Yeah.
student as well. Just to
Yes,
let you
I know. We talked before. I will take notes. Yeah.
And just one more question I have, like, you know, in your tensile test summary, you did mention that the strength is good because of the finer grains, but then when you concluded ductility, you said it is due to scattering. If there is a finer grain size, I mean, in generally, we as a metallurgist, we study a lot of strengthening mechanism. And one of the things I could remember from my days, you know, reading Harry Badesias and, you know, Phil Pragnell preaching that, you know, like the finer the grains, the only mechanism where you don't lose strength as well as increase the elongation is when you make the grains finer. And why do we get, you know, ductility still, although it is finer, it's larger. I mean, what I have also noticed practically, I mean, you did mention one point is defects, but even some of the things as we do deposit, I've done tons or if not, you know, thousands of CT scan. I can certainly say that there is no porosity with, you know, 20 micron resolution, voxel size resolution. I still don't understand why we don't get, you know, good ductility.
Okay.
I don't know if you have any opinion on that.
I think we actually currently we blame naturally occurring porosity. They are so small, and they are never reach the critical threshold by fractography, but they are in the wrong location because they were in the bulk and past the XCT. But when you make the dog bone is like hourglass shape. They actually exposed without our knowledge. We can't keep doing XCT, so we just say, oh, pretty good. Then we just went. But after fractography, we could always see one or two naturally occurring one, very small. I has to be a very dedicated person in the SEM room to find. So that not only cause the ductility loss, probably mainly cause the scatters in ductility.
I don't know.
I just came back from a conference it's dedicated to defects on fatigue. So the 3 days only talk about fatigue and the defects. So the general consensus I got is strength is not affected, but ductility is a big problem, and especially the scatter in ductility. So where do you draw the design allowables for the industry?
I mean, that's I think that is where we are also scratching our head. Anyway, thank you so much. I'll give other people opportunity.
Thank you for your question.
Ivan.
Hello.
Yes. Ivan Lorden, please.
Hi, thank you. Ewan Lorden, Jaguar Land Rover. Really enjoyed your talk, so thanks for that. My question was around, I guess, the effects of both residual stresses and preening on the, I guess, the solid state transformations that you were describing later on. So have you considered the combined effects of residual stresses and preening on the solid state transformations that you observe?
Yeah, I think that's a very good question. We always think we have no residual stress. Residual stress is negligible because the samples are extracted from very large part. It's not like powder bed fusion. They purposely build a small one near net shape. But after pinning will introduce deformation, hence residual stress. But we still extract the samples. So the samples are so small, the dog bone and the compact tension, they have 4 free edges. There's nowhere to hold the residual stress. So we measure the residual stress after pinning as well. We would say they are negligible effect on the property, especially for titanium. The strength is 1100 megapascal. The stress is around 20 to 50 megapascal. in that kind of scale. But for powder bed fusion, they always will do stress relief treatment.
Okay, brilliant. So then would I be right in thinking then that it would also have a negligible effect on the annealing process that you'd be proposing afterwards?
I didn't hear the process name you say.
Oh, so am I right in thinking that the residual stresses or the dislocations potentially introduced from peening would not affect the annealing that you proposed for the beta phase?
No, annealing is for titanium, high strength titanium, we actually go beyond the beta transient temperature.
Okay.
So we compared annealing of as-built and annealing of peened, and the microstructure are similar, but the grain, the columnar grains will be more controlled by applied peening.
Okay, brilliant.
Yeah. Thank you for your question.
Thank you.
Thank you.